So now we'll go into a little bit about vector and matrix products. So this will be the first numerical algorithms. And really these are quite important. So the communication costs and the efficiencies we'll derive for these are the building blocks for much of everything else in numerics. But we'll start out today fairly simple. We'll just, if we can get to it, do up to the matrix vector product. And then I think my plan is in the next lecture to do matrix multiplication, which in a way is a generalization of everything here. So the basic matrix and vector routines are available inside the BLAS library, which is good to know about because you really don't want to write one of these yourself because it'll just be way, way, way slower than what this library provides. And this is what's tuned on any given architecture. The BLAS are in Fortran, but could be used from any C++ code with a little bit of pain. So the kind of some examples of the routines that there are. So we have DAXD, so adding essentially scaling a vector, doing inner product, and doing a norm are the BLAS1 routines. These were historically developed first. They're the most primitive routines using which you can build up just about everything else. Then the BLAS2 routines were introduced, which work essentially with matrices. So at least with one matrix and a vector. So all of these will usually have just a single matrix involved as part of the operation and two vectors. These are things like matrix vector multiplication, things like the outer product, where we compute a matrix from two vectors, and things like the triangular solve, where we solve a simple triangular system of equations. So we do backward and forward substitution. If we go to BLAS3, we get things like matrix-matrix multiplication, which is a lot of outer products or a lot of inner products. We get many triangular solves, which is just more of these. And we also have maybe some other routines like rank K updates or symmetric matrices. Why would we need these? Is it just for convenience?
Well, like, need what?
The higher level BLAS.
Because they take better advantage of the amount of memory accesses, because in a matrix multiplication there's only n squared data, but n-cubed operations, so you would want to do O(n) work for every memory access on average.
Yeah, in matrix-matrix, right.
Yeah.
So while in matrix vector, we have only one flop per byte. So the flop to byte ratio is in general referred to the amount of work done for a given amount of let's say words written and read from memory. Also usually associated with basically the memory footprint. There's also no good reason. So both of these are one flop per byte. But BLAS2 is faster than BLAS1, substantially so. I'm trying to remember why. I live in this world and between these a lot of the time, as most people do. So you really want BLAS3 versus BLAS2, but in fact, these routines will get better performance than these. So you can do, for instance, a matrix vector product via many inner products, but you would be, you can't do that quite as efficiently. For instance, you would have to read the vector many, many times for each one of the inner products. But there's a nicer reason, too, that I at some point knew theoretically for the difference between these two, but it's not coming to me now. Maybe I'll remember it by next lecture. But in general, what we can say is that we can really assign almost different gammas, so different floating point rates to each one of these levels. And what we have is that the time to do a flop kind of for operations like this will in fact be greater than for these and greater than for these. So we have a better effective computational rate. This gamma 2 will essentially be correlated with the memory bandwidth that you have. This gamma 1 is actually worse, but gamma 3 is substantially better. So here we can actually hope to reach the floating point peak of the machine. If somebody comes up for why these are slower, let me know. Okay, but let's go ahead and start with the inner product. So what we'd like to do is something like X transpose Y, so and compute some inner product of these two. So what would this look like in terms of a problem we've already seen before? Have we already analyzed the efficiency of this thing? The sum reduction, right? It's pretty much the same, except modulo the fact that you have to do the scalar products. So the amount, then kind of to say the basic stuff, we have n inputs, we have n work, and we have and the time is proportional to that. This is basically as hard as doing the scalar reduction, and we've already done much of the analysis for that. So what we'd like to do is really, okay, multiply the scalars. Hopefully they, the ith members of these live in the same process, and we'll assume that, although life is not always that good. Then all we have to do is a summation, and we've looked at how to do reductions already. But let's kind of walk through that again so that we see the common patterns between these. What we generally have is that maybe we can define a little fine-grained task for each one of the x1, y1 variables, and what we'd like to do is combine these guys. So we have what looks kind of like a 1D problem, although it's not really a 1D problem in a sense that we'll see. From the fine-grained point of view, what we're doing is a local scalar product, and then we're doing a reduction. So if we want to agglomerate that, there's not so many different ways. In fact, a lot of the different ways would be equivalent because we don't actually care about the ordering of the x elements or the y elements, but only their relative relationship. One way we could do it is first agglomerate and then map the coarse-grained task to processors, although here agglomeration versus mapping aren't that different. We could just map immediately, so combine and then map. So it doesn't really help to have more tasks, more agglomerated tasks than processors, because things are generally quite parallel. So if we do this, then we're doing locally an inner product and then a sum reduction. So that may look familiar. For instance, when we did scans, something similar happened. And so are we reducing here then a subvector that every process contributes? So I guess, is the reduction a multi-item reduction or a single item reduction? Single item, yeah, it's just scale. So we do a local inner product, but then we just get a scalar out. Oh well, yeah. So for BLAS1 versus BLAS2, the latency cost, I think, is the difference. So if you do a bunch of BLAS1 operations in sequence, you can't do them as concurrently as BLAS2. So that's pretty trivial. But I thought I was trying to think of something more clever. But I think that's why, basically. Okay. Okay, let's get back to the inner product. So our computational cost is n over p. So this is the amount of work every processor does. The latency bandwidth cost then maybe depend on the network, which we haven't really touched on when looking at the binary tree sum. So on a 1D mesh, even the latency and bandwidth cost will be proportional to p. So that actually looks somewhat bad, right? So we would hope we would have a logarithmic latency cost, and we had a problem that looked one-dimensional. We really shouldn't think of this problem as one-dimensional. We should think of it as a tree-like. So what we'd like is a network that into which we can embed a tree. We cannot embed a tree without overhead into a 1D mesh. So there will be some slowdown if we try to do this one-dimensionally. And in terms of, for doing the reduction, we can't do much more clever than just kind of pass these scalars along through one process, maybe in the middle. So this would be like p over 2. For a 2D mesh, we again need to build some sort of spanning tree and propagate the scalars through that spanning tree. That spanning tree will have depth proportionate to square root p, really something like 2 times square root p, which is still not better. And in general, kind of our spanning tree will have depth proportionate to the diameter, and so really the diameter of the network decides how many hops we need to travel. Or well, half of the diameter. For hypercube, we have log p, which is also optimal. So our ideal tree can't be of depth any less than that, so long as the branching factor is 2, or so long as if we look into the kind of time complexity, so long as we can't send more than one message at a time. So if we can send P messages at a time, then we would, so if you did have a machine that could send P messages at a time, what's the right way to do this algorithm in practice? What does the tree want? So if every processor could send P messages concurrently at the same cost as sending one message, so basically let's say we have a fully connected network and we can actually, we have network hardware that can operate all those links simultaneously. What's the fastest way to compute a reduction? Not a realistic
Send
argument.
to one
Yeah,
processor.
send everything in one processor, yeah. So basically have a reduction tree that is height 1. And if we're sending a message of size 1, for a very large P, this will still be reasonable, right? So there is overhead in the sense that this processor will receive a total of P data. So in our model, that's a reasonably big communication cost. But if P is 1,000 and N is 1,000,000, you can send all those messages at once. You should. So sometimes the basic intuition is also if you have really tiny messages, kind of thinking of things in terms of I can send only one message at a time is maybe not quite right. And on many networks, you can have more than one message effectively in flight more efficiently than what our model provides for. So it could make sense to have more direct communication and actually get high performance. Okay. But so long as we assume that we can only send or receive one message at a time, then our cost will have a log factor in it because we need some spanning tree that has to be executed in kind of logarithmic time. And our cost will look like this. We can throw out the bandwidth cost terms because beta is much smaller than alpha. So for a 1 byte message costs as much to send as a 0 byte message in practice. So, and the efficiency and scaling we will not do because in terms of this cost because we did that basically in the last lecture. It's the exact same. But we can look at what happens to that efficiency if we try to do a particular network. So for a 1D mesh, we had this alpha P term. So we have to wait for P messages effectively in time. And again, we set a constant efficiency, so we set U of PS constant itself for PS. What we get is 1 overhead term where we want PS to cancel out N. So we need PS to be the square root of all the other stuff. So again, very similar analysis, which basically tells us that we can strong scale to something like square root of N processors, where N is our kind of starting size, and also have some dependence on this usual ratio. If we look at weak scalability, as usual, we can go further. So to analyze this, we just substitute for this N something different, and what we end up with is that this term grows. So basically, we cancel one of the P's, so we don't have to take a square root. So we can weak scale to potentially the square of the number of processors in the 1D mesh. On a 2D mesh, okay, we have a different term here. We do the exact same analysis, but we end up with a different power of P. And if we want to strong scale, we again need P of S to cancel all the other terms here, figure out how many processors we can strong scale to, so we can get to N to the 2/3 number of processors. Actually, let's see if we have an intuition for this. So we start, let's really go back to the 1D mesh, because I'm just giving these numbers and I'm not really explaining what that means, right? So we have a 1D mesh and we can strong scale it to something that's proportional to square root of the local size. So yeah, in a sense, and it's hard to get an intuition for. So our latency overhead basically grows with the number of processors, while our local computation time decreases with the number of processors. So I think the square is coming from the process of these two growths. So the gap is growing like a square, and so we get this kind of square root dependence. While as we weak scale, we keep constant the time spent doing the local computation, the local inner product, while the time it takes to do the reduction across processors is growing by a factor of p. So we get kind of a linear dependence on n. We kind of, as we grow the number of processors, we outweigh the time that we were originally, that's actually scalable linearly. While here, that time diminishes as kind of a square function. So a little bit of intuition, but it's not so critical. And here again, I think we can think of it based on relative growth of terms in length is not all that good. And if we look at the weak scalability, again, a similar analysis, but now we can grow to a problem that is, we can weak scale to the number of processors is proportional to the square of the problem size we had on one processor, which is because as we increase the number of processors, we spend the square root of the number of processors more time doing the reduction, because we have this, what used to be a square root p alpha term, so that if we take the number of processors to n squared, then we'll be doing, this will be proportionate to n in terms of the latency cost. Okay, does that make sense? More or less? Okay. So now let's go to a BLAS2 operation, the outer product. So now we want to do xy transpose. And so this essentially takes every one of the elements and multiplies it by every one of the other elements. Outer products by themselves are not such a common thing, and we'll see why shortly. But one related problem to this that's of more importance is molecular dynamics-like problems where you do particle-particle interactions and you compute all the forces. Then you can think of all pairs as what the outer product does. So we're here combining kind of all pairs and computing something between them. This is kind of the simplest thing we can do is multiplication, but if we wanted to compute a force matrix between particles, we would do something like this. And we'll come back to the fact that one never really wants to compute a matrix. The fundamental problem here is perhaps the imbalance between input size and output size. If you can feed this back into a vector, you're very happy. So in a molecular dynamics simulation, that's what you do. You compute all the forces, and then you act using them onto your vector, and you get a new vector, a new particle location. And that problem actually can be done different computationally and in parallel. But okay, let's work for now with this guy. So, and there is an analog of it that is extremely important. Okay, so usually we have n-squared multiplications, and we'll treat our input size as the output size, or we can redefine the problem the BLAS way. Yeah, you really want to think of M1 as the memory usage of data. So the input size should not be taken too literally. So we partition in a natural way by assigning fine-grained tasks to each one of the scalar multiplications. Then effectively each one of the fine-grained tasks needs one of these x's and one of these y's. So assuming no initial replication of data, so if we're given a vector element on only one processor, then we have this many tasks that first store the actual vector elements. Here we'll assume that the diagonal somehow stores these. So task II stores both xi and yi to start with. That's a fairly arbitrary assumption, but nothing much changes if you do it differently. We have then the communication is essentially our diagonal task, which owns xi, broadcast to everything in that row. And for YJ, we do the same, but a picture will help much more. So we have these, they're underlined where they start, and then the arrows point to where they need to go. So for X and Y. So a commonality of all of the BLAS problems and much of tensor algebra is the replication in one dimension and the other dimension of elements. And this is a type of communication pattern that we'll deal with extremely often. And it's nice to understand it. And one thing that is kind of hidden in this picture is that this communication pattern, again, shouldn't really be thought of as linear or as a kind of 1D, because you really have a broadcast, and so you have one talking to many, not these talking in sequence. So we don't have to pass here, then pass here, then pass here. And that distinguishes a problem like this, for instance, from some kind of stencil application, where if you model it through time, you will actually see, okay, we have to, through the number of iterations, we have to pass to our neighbor, then the neighbors have to pass to the subsequent neighbors, and so on. So you have actually a communication pattern that kind of looks exactly like this, and you can't do much about it. But in Dustin algebra, you can kind of do broadcasts, which fundamentally change how things are parallelized. So these are basically two different types of dependency graphs. Okay, so this is again the algorithm. We have a horizontal broadcast and a vertical broadcast, and then we do scalar products. So this is a fine-grained algorithm. So then we'll try to agglomerate this. So essentially go from a PRAM style algorithm to something that makes sense in distributed memory. So for 2D, we'll combine into little blocks. For 1D, we have two choices. We can take rows and columns, and they won't be very different. Just transpose the problem. So for each task, we now need to do a broadcast. And so now this will be, in the agglomerated case, a multi-item broadcast. Is the cost of a multi-item broadcast the same as the number of single-item broadcasts multiplied by the number of items we're broadcasting? The number of items times cost of a single-item broadcast. What is different? Anybody remember? So if you want to broadcast a message of size n from one processor to all others, how much cheaper is that than broadcasting n messages of size 1 in sequence?
P latency versus log P latency.
Well, n latency, I guess. True. What if we could do them even concurrently somehow? So what if we just take a single item broadcast algorithm and make the item of a larger size by a factor of n? Is that as good? The latency should be fine.
So if it's one single message, it can be further broadcast until one is done. But if it's multiple messages, and the receiver can begin to send messages once it's received the first one, so that saves the time.
Right. So we can pipeline. So we can use smarter algorithms. So how much does that save us? Did this in a fair amount of detail. Some of you guys are remember this. It's also in detail covered in the chapter on this. So we can't really reduce latency cost, right? There's no flops cost to speak of. So it's the bandwidth cost that we care about. So what would be the bandwidth cost if we did a single item like broadcast with a huge item? Let's say that item has size n.
N times beta.
N times beta for the single item case?
For the largest.
For the large message, but I guess if we forward that message to one processor at a time via some spanning tree, we have to multiply it by the depth of the spanning tree, right? So then what would be the bandwidth cost for a fully connected network or a Hyper-V. And 10 block B. And so what can we get if we have a better algorithm, a pipeline algorithm, or a butterfly algorithm?
It's just log.
Just done. Not like B. We have to send that data out of the root. But we can get linear cost in N. I do expect you guys to know that. I don't expect you guys to necessarily know the details of how the algorithm works, but it's important to remember that broadcasts and all of the other collective operations can be done in linear bandwidth cost with the message size, not something that's unlocked. And you will see often in literature people actually make this mistake. They don't know about the algorithms that are faster. And it's quite annoying for people who actually want things to be optimal. Okay, so let's quickly do a little bit of the inner product. If we agglomerate in 2D, we have a communication pattern that looks something like this. So now we are essentially broadcasting left and right, but sending more data. So two entries of X and 2 entries of Y in each dimension. And that actually will produce a better cost. If we have a 1D agglomeration, then we are communicating potentially horizontally, and then we have kind of one guy send a single scalar entry to every other processor. So what is actually this communication pattern? Scatter? So we have X that lives on not on one. So if we had X that lives on this column to start with, then it would be a scatter this way. But here we have that things are starting in the diagonal, so underlined. So it's something a little bit different. What communication collective is this?
It's an altogether with X, right? Because you want all the X1 through X6 to be on every processor, right?
Yeah, that's true. So you need to receive a message from every other processor on every processor. Yeah, so it's an altogether. So, so are we happier with an altogether or a it's actually not a scattering to start with, it would be a broadcast, right? So if X lives, X lives here to start with, and we want to get to all our processors, it would be a broadcast. Are we happier with an all-gather or a broadcast?
Altogether.
All-gather, yeah. Cool. So you all-gather for the butterfly algorithm costs half of the much of the broadcast. Okay. I think before we go further, I should stop because we're past the time. So we'll, I think, continue the outer product next time and then start with matrification on Tuesday.